And here's the new part. 1 mole of aluminum carbonate, 3 moles water. This is your coefficients from the reaction. For every 1 aluminum carbonate that gets consumed, 3 waters get made. And then since we want our answer in mass, then we need to go to the molar mass of water. One mole water. Calculate its molar mass from the periodic table. The coefficient of the reaction in the reaction is a 3. It came from our balancing. It's the coefficients of just those 2 materials. We're ignoring everybody else. But it's the coefficients of just those 2 materials. For every 1 aluminum carbonate that reacts, 3 waters are created. We're doing molar mass relationships, but this time we're doing it through the course of a reaction. And the key central part of the calculation then is that reaction, the proportions in which they react and form. And then you do the math. And you should end up with something like 2.31 grams. Give or take a little for rounding. Question about that calculation? All right. This number that we just calculated is really a prediction. It's called theoretical yield. And by definition, this is the predicted amount of product that you should be able to make. Or sometimes it's defined as the maximum possible amount that you could make. But what we did in this calculation was we assumed that all 10 grams of this would get reacted. And if all 10 grams react, then 2.31 grams of water should be made. Should be because, you know, in practice, reactions don't always go the way they're supposed to. Because getting that 2.31 grams of water means you would have to be certain that every single molecule of aluminum carbonate reacted, and every little molecule of water that was formed, you collected. None of it spilled, none of it evaporated or anything like that. Everything would have to go perfect in order for you to actually get that amount. That's the calculated amount that it's possible to get. There's this other thing called percent yield. And this is a measure of efficiency, really. And by definition, or by formula, I should say, it's the actual yield that you get by doing the reaction divided by the theoretical yield times 100. Now, here on the board, and you with pencil and paper, starting with this 10 grams, you all calculate 2.31 as your predicted. You all would have the same theoretical yield. But if you went in the lab and did this, no two people are probably going to get the same actual yield because you do things different. Things happen a little bit different. Actual yield is an experimental number. Theoretical yield, this is a calculated prediction on how much could be made, but the actual yield is experimental. So if 2.31 is what's possible, naturally the closer you get to 2.31, the better you've done. And so percent yield is a measure of efficiency. The second part of problem 1 says if the reaction is performed and 1.96 grams of water is actually collected, then calculate percent yield. To calculate percent yield, you divide what you got by what you should have got, and then you multiply that by a number. Actual over theoretical. Question about theoretical yield or percent yield.
Yeah, can you give us theoretical yield efficiency?
Theoretical yield is not efficiency. Percent yield, this is efficiency. The closer that percent yield is to 100%, the better you've done. Question.
So it's going to be 1.96 divided by 2.31 and multiplied by 100?
Yes. Question. All right. Question number 2. What's the difference between question number 1 and question number 2? There's a limited amount of HCl. In the first one, we knew for certain we had extra HCl and that all 10 grams of aluminum carbonate could react. But now, given numbers for both of them, we don't know that. If those are absolutely perfect amounts where they react exactly, and there's no leftovers of anybody, then that's a rare fluke. Don't count on that. More than likely, we're either going to use up all the aluminum carbonate and have some HCl left over, or use up all the HCl and have some aluminum carbonate left over, but just by looking at it, it's not obvious which is which. Correct? We got numbers for each. This is what's called a limiting reactant problem. And it's really not a different kind of calculation than what we did before. When we knew that all the aluminum carbonate would get reacted, then we worked it out and predicted the amount of water. This time, when we don't know for sure which one's going to get reacted, we just do them both, calculate them both. It's going to make it longer, but it's not going to make it a different method. When we knew it was going to be aluminum carbonate consumed, we made a prediction. When we don't know which one gets completely consumed, we make two predictions. And at the end, we'll calculate, or we'll compare them. But each of these parts is exactly like we did in problem 1. Here's the aluminum carbonate part, exactly as it looked in problem 1. And here's the HCl part. That goes exactly parallel to the aluminum carbonate. A lot of times people have trouble with limiting reactant problems, and that's because they try to have one method for the regular problem and a different method for limiting reactant problems. You don't need a different method for limiting reactant problems. All we're doing here is the same thing we did in that very first problem, except we're having to do it twice to make two different predictions. And we'll talk about those two different answers in a moment. But is there any question making those two parallel predictions? Yes?
Where's the 6 moles of HCl?
That comes from here.
And we're using it this time because there's a...
On this part, on this lower portion, we're trying to relate HCl to water. And so that's a 6:3 ratio. Whereas in the previous part, it was a 1:3 ratio. So it really just depends on what you have there as your ratio, depends upon the two materials you're relating. It's going to be their coefficients ignoring everyone else. The top one goes from aluminum carbonate to water, and the bottom one goes from HCl to water. So what we've got now, 2.31, 2.47, that's two separate predictions about how much water could be produced. We've got enough HCl there to make 2.47 grams of water, if it all gets consumed. Key word being if. if all this reacts, you can make 2.47 grams of water. But if all of the aluminum carbonate gets reacted, you can only make 2.31 grams of water. You've only got enough of it to make 2.31 grams. And considering when you start this reaction, you don't have any water yet. You've got 0 grams when you start, correct? And as the reaction goes, the water's produced and you start to accumulate water. It goes from 0 grams to 1 gram to 2 grams to 2.1 and 2. And you're going to get 2.31 before you do 2.47, correct?
Yes.
And at that moment, when you get 2.31 grams of water produced, everything stops. Because at that point, you will have run out of aluminum carbonate, and it's not possible to go beyond that. So you make these two predictions, and then you key in on whichever prediction happens to be lower. Because that's the realistic amount. That's your theoretical yield. The lesser of the two predictions is the theoretical yield. The higher number, that's just simply not possible. HCl turns out to be in excess after all. We've got more HCl there than we can react. We didn't know that going in when we had numbers for both. And so we did two parallel calculations, knowing that in the end, whichever one predicts out to be the lesser quantity, that lesser quantity is the theoretical yield, and the reactant that gave you that lesser quantity is called the limiting reactant. That's the one you run out of. That's the one that limits the progress of the reaction. We'll use up all of our aluminum carbonate. We'll have some hydrochloric acid left over, and if everything goes perfectly, we'll have 2.31 grams of water. Capital if. Any question about that? Do you see how that's only a very small modification of that first original problem? It makes limiting reactant problems longer than the regular ones, but not a different method. Maybe that will help you. So the next part here is sequential reactions. And we're starting off with this same aluminum carbonate reaction that we've been working with. What's different in this situation is that we don't stop with just that one reaction. We've got a sequence of 3 reactions that are involved in the overall process. And question number 3 is asking, if we start with 10 grams aluminum carbonate, then how many grams of ammonia could be produced? assuming excess of all your other reactants. So the two materials we're trying to relate are aluminum carbonate and ammonia, and they're not even in the same equation. Well, you can only relate things if they're in the same equation. Aluminum carbonate doesn't make ammonia, at least not directly. The aluminum carbonate reacts with HCl to form aluminum chloride and water and carbon dioxide. Look at these three products. And look at the reactants in the next step. Water, water, correct? So what that's telling you is that the water that's formed in reaction number 1 goes on to react in reaction number 2. It's not just formed and sits there, it goes on to react again. So that's the common link between reaction 1 and reaction 2. The water that's formed in the first is consumed in the second. What relates the second equation and the third equation? The hydrogen. The second reaction forms hydrogen, the third reaction consumes it. Now, a while ago I said that everything on the left of the arrow was considered reactants and everything on the right was considered products. That's technically true. But when you have a sequence like this, you've also got some things that show up as both. And more in particular, they show up as a product and then as a reactant. It's formed and then later consumed. This water is not one of your original reactants, and it's not one of your final products either. The water is formed for a moment, and then it goes on to become other things. It's a product, then a reactant. It's called an intermediate. The hydrogen is also an intermediate. Intermediates are not true products or reactants. They're a temporary stage that you go through in changing from reactant to product. Intermediates are a temporary stage that they go through. It will always appear as a product first and a reactant later. Formed, then consumed. It's only there for a flash and then gone. So looking at everybody on the left side of these reaction arrows, how many reactants do you have? Actual true reactants? 4? Because these are intermediates. You add this, and you add this, and you form some stuff. Then you add this, and it makes some more stuff. Then you add this, and it finally makes ammonia. You've got 4 reactants. How many products do you have? Also 4. Aluminum chloride, CO2. Well, I guess it's more CO2. So 3, right? Aluminum chloride, carbon dioxide, and ammonia. You've got 3 products. It looks like 4 because this one forms carbon dioxide and this one forms some more carbon dioxide. But that's actually just 3 substances, right? Aluminum chloride, carbon dioxide, and ammonia are 3 products. The water and the hydrogen don't count. The water and the hydrogen are intermediates. Now, they're the intermediates physically as far as what converts to what, but they're also your intermediates mathematically when you try to set this up and do the calculation. You can't go directly from aluminum carbonate to ammonia because they're not in the same equation. And those coefficients only mean something within the context of their own equation. So this calculation is going to look a little different too. It's going to look like this. We start with our 10 grams of aluminum carbonate. We want to ultimately relate that to ammonia, but like I said, we can't do that directly. We have to do it indirectly through those intermediates. So step one is to get out of grams and into moles. Once we're in moles, we can go to the balanced equations and start using coefficients to relate one substance to another. And in the top reaction, we need to relate aluminum carbonate to water. 1 mole of aluminum carbonate reacting means 3 moles of water formed. And we're relating it to water because that's the common link between the first reaction and the second. In the second reaction, we'd be relating water to diatomic hydrogen. 2 moles of water, 4 moles of hydrogen. That allows us to get to the third reaction then, where the coefficients are 3 moles of hydrogen, 2 moles of ammonia. And then since we want the answer for ammonia in grams, 1 mole of ammonia -2.91. The part in the middle, the part that's in orange, that's the new part. Since we have to wind our way through 3 reactions, we wind up with 3 mole ratio terms. Because we have to relate indirectly through those intermediates. We can't compare aluminum carbonate to ammonia. We have to compare aluminum carbonate to water, water to hydrogen, hydrogen to ammonia. Those intermediates are your links physically and your links mathematically, and that's what adds to that center section of the problem. You got to kind of stagger your way through the intermediates to get to your final prediction. But notice, we're not just picking coefficients here and there. This 1 and this 3, both of those came out of the first reaction. And this 2 and 4 were both out of the second reaction. These were out of the third reaction. You can never take a coefficient from one reaction and a coefficient from another reaction. It's completely out of context. That'll never work. So what we're using is 1 to 3 as the first term, 2 to 4 as the second term, and 3 to 2 as the third term. You've got to be consistent and only pull out of the one reaction. Because those proportions lose meaning if you get them out of context. Do you see how this is like problem 1, only a little fluffier there in the middle because we had 3 reactions to deal with rather than 1. But otherwise the method is the same as in that first original problem. If you had to wind your way through a 5 reaction sequence, guess how many terms you're going to have in the middle? 5. But otherwise the method is the same. Question there. Question number 4. Is still dealing with this same sequence of reactions. And it's saying how many molecules of CH4 are needed to react 5 grams of nitrogen. Here's nitrogen, and here's CH4. For this particular problem, do we even need this first step? No. All we need to do is relate these two, correct? So if we're going to be using 2 reactions, we're going to have 2 mole ratio terms. Starting with the 5 grams nitrogen. Working your way towards CH4 using just the second and the third reactions. Go ahead and do this on your own. See what you get.